During this the 9th week, I will be discussing on a very important topic, that is design for reliability. Even the next week, that means during the 10th week, I will be continuing discussing on design for reliability. Okay, now during this week there will be 5 lecture sessions, and let me first tell you what are the topics I have included in these lecture sessions. And these topics are all related to reliability. So in the very first lecture, I will be discussing the basic concept of reliability, general reliability function, MTTF, mean time to failure, variance, instantaneous failure or hazard rates function. In the subsequent lecture, the lecture 2, I will be discussing on the general reliability function, cumulative and average failure rate, bathtub hazard rate curve, probability distributions to model failure rate, exponential reliability function. This will be the coverage during the second lecture. In the third lecture, I will again continue discussing on probability distributions in modeling reliability with a set of numerical problems. In lecture 4, reliability of systems we will be talking about, and there are different kinds of systems. So this will be the first set of the systems for which the reliability modeling will be discussing: series and chain structure and parallel structure. And in lecture 5, we will take up several typical numerical problems related to reliability. Now let us first discuss the concept of reliability. In the next half an hour or so, I will be discussing the concept of reliability. Then what is this general reliability function, and related to general reliability function, what is MTTF, what is variance, what is instantaneous failure or hazard rates function. Okay, so this will be my coverage. Now, what we have done in all earlier lecture sessions. This course is on quality essentially. So in all earlier lecture sessions, we dealt with quality principles in design. There are many kinds of principles, and explored the notion of quality during the product design or during the manufacture of the product or rendering of a service. So this was our coverage. We have been discussing on different kinds of tools, techniques for quality control, for quality improvement. Okay, some of these tools to be used during the design phase of the product, or many such tools and techniques you are required to use during the manufacturing phase. Now, all these discussions were limited on a specific instant in time. It means that whenever we try to define quality, then we have defined quality, we have measured quality, but all these the measurements are valid at a particular instant of time. That means at time t equals to t. In this session, we introduce the concept of reliability. Now, what is this reliability? That means in plain and simple terms, reliability means the quality in the long run. That means at time t equals to t, you say that a product is a quality product. Okay, that means one or more dimensions of the quality are made available in acceptable say the levels. But then the product is to be used for over a time period. Now the reliability actually tells you, or the reliability analysis will lead to a conclusion the whether the product will be performing as per the quality requirements. Okay, even after say a few time periods, maybe after 1 month, maybe after 1 year. So that sort of the prediction you have to make. That means the quality in the long run. So whenever we refer to reliability study, the reliability study deals with the random occurrences of undesirable events, failures during the life of a physical system. We are concerned about the life of the product, and whenever we refer to reliability study, we say that during the life of the product, okay, there could be many random occurrences of undesirable events, particularly the failure. It might fail at any point in time, whatever may be the design level of a particular product or a system. Okay, so reliability is a measure of the quality of the product or a process over the long run. This point I have already emphasized. The concept of reliability is related to an extended period of time over which the expected operation of the product is considered. We have already referred to the functional value of the product. Now, in any reliability analysis, we need to conclude whether this functional value of the product or the process or the system is assured over a period of time. Is it okay? So that is the basic focus on any reliability study. So now, how do you define reliability? So the reliability of a product or a system is the probability that when operating under stated environmental conditions, is it okay? That means any product when you design, you say, why don't you start using it? So as per the design specifications of the product, now this product is supposed to be used in a stated environmental or working conditions, work environment, that is to be mentioned. Now the product or the system will perform its intended function. Is it okay? Like say, when you say it's an automobile car, that means I know that when I start using the car, which particular function actually you are trying to get, okay, from car. So that means what we expect, that the product will perform its intended function adequately as specified in the design norms for a specified interval or period of time. So that means when you try to quantify reliability, there are 4 issues to be looked into. First one, it's the probability. Then the second one is related to a particular product. Is it okay? So there must be some stated conditions in which a product is supposed to function. Then the intended function of the product must you specify. And the fourth one is, whenever you talk about reliability, that means you must be able to specify the time interval or the period of time. So whether it is 5 hours or 500 hours, you expect the product to run. Okay, so this is the objective definition of reliability. Now, in the broadest sense, reliability is a measure of performance. Getting my point? As we have mentioned, that the quality has got several dimensions. So one such dimension is one of the important dimensions is the performance. So the performance in the long run. So essentially, the reliability is a measure of performance. Reliability is applicable to various types of human activities as well as to the performance of physical systems. This is obvious, in fact. That means it is a concept which is applicable not only for say inanimate object, but also for animate object. Okay, in the broadest possible the sense. Now whenever you study reliability, whenever we try to model reliability for a systems or for a product or a process, a varieties of terms, okay, you need to use. So a varieties of terms are used to denote the system or the entity under study. The terms which we will be using, that is unit, part, component, device, equipment, subsystem, element and system. These are the terms most commonly used interchangeably. Okay. So we'll talk about, we'll referring to all these terms and terminologies whenever you try to the model the reliability. System reliability is the probability that the system will perform its intended or required function for a specified interval of time under stated operating conditions. That means either you define the the reliability with respect to the part or the component or the product, or in many a time we are really concerned about the system reliability. Okay, so the same definition applies with respect to the system, and you know what is the definition of a system, is it okay? So it is the probability of a non-failure over time. There is another way you can look at. That means if it performs, that means there is no failing of the component during a specified time period. You say with respect to this specific time period, the reliability is very high, or the reliability is almost 100%. Reliability is closely associated with the quality of a product and therefore can be considered as a subset of quality. Now the question remains, like suppose the quality is excellent. We say that the product quality, systems quality is excellent. Can you assume that the reliability of the systems or the product is 100%? That means that the probability, it's essentially is a probability. Can you assume that the value of reliability is 1? So that is a big question in fact. But at this point we should highlight a particular aspect, like whatever may be the quality level of a product, is it okay? That means it could be very, very excellent. It's the best product created, but there is no guarantee that it will not fail. If it may not fail, say within the next 5 years or within the next 10 years, but beyond 5 years, beyond 10 years, at any point in time it might fail. Is it okay? Because at the time passes, maybe the performance is significantly affected by the external noise factors on which you may not have any control. Is it okay? So we never say that that the quality of the product is so excellent that the reliability is 1. Is it okay? So that means we presume that whatever may be the level of quality of a system or a product, today or tomorrow, at any point in time in future, it may fail. Is it okay? So that is the basic assumptions we make while we model reliability. Reliability, on the other hand, is concerned with how long the product continues to function once it becomes operational. That is most important in fact. That means suppose the machine is installed and then it becomes operational. Then you have to conclude or you have to predict how long it may perform. Is it okay? So that is also, whenever you ask this question, essentially you are referring to the concept of reliability. A high quality product will have high reliability. So this is an hypothesis. Is it okay? So that you have to prove. Is it okay? And sometimes it may happen that you have defined high quality product, or you have manufactured a high quality product at only for the instant of time, but you are not sure whether the next instant of time, whether it will perform or as per the requirements or not. So there could be many such cases. So we should know what are those systems existing at your workplace. Reliability can be viewed as the quality of the product's operational performance over time, and so that basically there is a time dimension, and therefore it extends quality into the time domain. Okay. Now let us now talk about once the concept of reliability is known, okay, then let us talk about the general reliability function. So how do you mathematically you represent reliability. Okay, so we'll proceed slow, but we'll try to highlight all the important issues, all the important functions, okay, or the important concepts related to modeling of reliability. Now let us first concentrate on this. That means how to represent the reliability function. If we represent the time to failure of a component or a system by the continuous random variable. Now the first thing, that means the first the variable you need to consider, that is a random variable, that is time to failure. That means you start the process has started working or the product has started working. Now it will fail either at a particular time period, and this time to failure is obviously is a random variable, and we are assuming that this failure is occurring due to some random causes. Is it okay? It's not like say due to some assignable causes. Is it okay? So that is the first assumption. Is it clear? I think it is clear. That means this time to failure, if you assume that the time to failure is a random variable, we are assuming that it is failing due to some random causes inherent in the system. So that is the starting point. Suppose this random variable is t, then t is greater than equals to 0. Is it okay? Then the reliability is defined as, that means reliability that the component or the part or the systems or the product, is it okay, will run for t time period, and that is the probability that this time to t failure will be greater than or equals to t. That means at least t time period, okay, the component or the part or the system will survive. Is it okay? So sometimes it is also referred to as the survival time. Now in the above expression, that means this is the expression, that means the probability expressions, it is assumed that reliability should be greater than equals to 0. When at time t equals to 0, that means at instant of time, is it okay, it is 1, that means it starts working. And obviously when the time the t tends to infinity, obviously this reliability will be 0. Is it okay? That means suppose it's related to the machine, what we are assuming at infinite time period, okay, from today, from the instant of time when it is installed, obviously reliability will be 0. Is it okay? So that is the basic assumption. Hence RT represents the probability that the time to failure is t. Therefore we can define the probability that a failure occurs before time t. Is it okay? So what is Ft? Ft is 1 minus RT. Is obvious. So probability that the failure occurs before t. Is it okay? Suppose between 0 and t. Is it okay? Less than t. So where F0 is 0, is it okay? That means it has not failed at time t equals to 0. But at time t, it has failed. Is it okay? That's why it is 1. Is it clear? That means there is a definite conclusions. In the last equation, RT is known as the reliability function. Is it okay? I repeat, RT is known as the reliability function, and Ft is the cumulative distribution function of the time to failure distributions. Is it okay? Like related to when we started discussing quality, we have mentioned, if you refer to, like say when several kinds of the distributions we have referred to, like say distributions for the discrete random variable, the distributions for say continuous random variable. Now obviously for continuous random variable you have the probability density function, and for discrete random variable you have the probability mass function. So for both the cases what you need to do, that means the cumulative distribution function, okay, of the time to failure distribution. Is it okay? That means the time to failure density function you first must know. So this is basically the density function Ft. Is it okay? It's a continuous random variable. So if you differentiate what is this is the cumulative distribution function. So ddt of Ft is nothing but minus dRT by dt. Is it okay? So this is directly you get if you look at the previous equation. So this is the probability density function, right? Ft describes the shape of the failure distribution. Is it okay? That means distributions will have a shape where Ft is greater than or equals to 0, and obviously integration 0 to infinity Ft dt will be 1. Is it okay? Fine. And if Ft is given, then capital Ft is 0 to t. Is it okay? That means up to t time periods. So Ft dt and Rt is equals to t to infinity Ft dash dt dash. Is it okay? So Ft dt. It should be noted that both represent the areas under the curve defined by Ft. Is fine. Since the area under the curve is equal to unity, we have always Ft lies between 0 and 1. Is it okay? 0 included, 1 is also included, and similarly Rt, that means the reliability function, is also lies between 0 and 1. That means what we conclude as far as reliability is concerned, so any value between 0 and 1 you may come across. Okay. Now one important measure related to say reliability function, is it okay? That is mean time to failure. So we say that if the mean time to failure, okay, it is one of the measures, you get an idea about reliability of the component. So if the mean time to failure is more, you assume that the reliability is more. Is it okay? So if the mean time to failure is less, you say the reliability is less. Is it okay? Now how to compute the mean time to failure? The mean or the expected value Et of the probability distribution function Ft of the continuous random variable time is this MTTF, that means T into Ft, that is the average value, T into Ft. Is it okay? So 0 to Mt, that is the MTTF. So from these equations we get 0 to infinity minus ddt of Rt T dt. Is it okay? So that means this Ft is replaced with these notations. Okay. So this is just a manipulation, and then if you go for integration by parts, what you find that MTTF is these expressions minus T Rt 0 to infinity plus these expressions 0 to infinity Rt dt, and ultimately you get these expressions. So MTTF 0 to infinity Rt dt. Is it okay? And with a note that limit t tends to infinity T Rt dt is these expressions equals to 0. Is it okay? And 0 into Rt, obviously it is 0. Is it okay? So we have the expression for MTTF. Also the mean time to failure is defined as this. That means level is a T median. Is it okay? That means there is a midpoint. Okay, that could be the 0.5. So the probability that T is greater than or equals to median. So okay, so among several values you have, so one value at the midpoint, that is called the median value. Okay, with respect to the time to failure, that is T. Okay, and the mode, that is the most likely observed failure time, that is given by Ft mode equals to maximum between 0 to infinity. T lies anywhere between 0 to infinity Ft. Is it okay? So so you have the expressions for the reliability that the component will survive is okay up to T median, and what is the corresponding say the failure time, that also you can compute. Is it okay? Okay, so mean, median and mode. Then there obviously the next one is the variance, and the variance is often used to describe a failure distribution. So it is defined as this one. Is it okay? The variance, that means mean time, that is the usual definition of the variance we have applied. That means the T is basically the random variable. So the T minus MTTF square Ft dt, 0 to infinity. Is it okay? And variance gives a measure of the spread or dispersions of the failure times about the mean. Is it okay? Already we know that the variance is one of the measures for dispersion, or the dispersion measures. So what is the expressions for the variance? Is it okay in this case? So obviously you have these expressions. Okay, So directly you can derive these expressions. Okay. Now, so if you simplify these expressions following these steps, I have given all the steps one by one. Is it okay? So it will help you understand that how do you get the final expressions, and ultimately you get you can relate it to the MTTF, and this is just 1, and hence the sigma square is this. Is it okay? So this is all these steps I have mentioned. Please go through them, and and if you follow the steps, you will come to know that how a particular expression has been derived. Is it okay? Now I will be highlighting another important the aspect, that is the instantaneous failure or hazard race function. Sometimes this is referred to as the failure rate function, but instantaneous failure or hazard race functions you need to define in any exercise on reliability. So how do you define that? Okay, so the probability of failure occurring in interval of time, say between A and B. Is it okay? Say between say 0 to 100 hours. Okay, so A is 0, B is 100. So how do you define it? That means the probability that this time to failure will be between A and B. So this way you represent. So this is FB, the distribution functions. Okay, cumulative distribution functions up to B minus cumulative distribution functions up to A. So this is RA minus RB. Is it okay? You just refer to the relationship between the cumulative distribution function and the reliability function. So obviously it will be from A to B FT dt. Is it clear? So this is very, very clear. So I'm just following the fundamental principles. Therefore, so what is the probability that it will fail between T and T plus delta T, instantaneous failure T plus. So RT minus RT plus T, right? The conditional probability of failure per unit of time or the failure rate. So that we define like this. That means it fails between T and T plus delta T. That means within T period, and obviously this probability is proportional to delta T. So RT minus RT plus delta T divided by RT. Is it okay? So then we have this the lambda T failure rate functions. So limit delta T tends to 0, and you have these functions. Is it okay? So this is minus ddt of RT and into 1 upon RT. So this is basically FT and FT divided by RT. So lambda T is nothing but FT divided by RT. Here it is known as the instantaneous hazard rate or the failure rate. Is it okay? So the lambda T is known as the instantaneous hazard rate or the failure rate. So if you refer to this particular equation, you will find that lambda T dt is equals to minus dr dt. Okay, so this is 1, and if you integrate both the sides, you will get these expressions, and ultimately you follow these steps and you will get these expressions. RT is equals to exponential, okay, e to the power minus 0 to t lambda T dt. Is it okay? Lambda T dt. This equation is used to calculate the reliability function RT when the hazard race function is known or given. Is it okay? So we have defined what is the hazard race function. Later on we will explore this one, and here we have defined what is MTTF, mean time, and subsequently we have proceeded to the variance. Is it okay? Now here one important the issue I should highlight, like say the MTTF is definitely one of the measure for assessing reliability, but another measure many a time we also refer to, that is MTBF. So MTBF is essentially it is mean time between failures. Now whether so MTTF and MTBF they are two different terms under certain condition. Is it okay? So MTTF may be approximated as MTBF. Now the condition is that whenever there is a failure occurring, so what do? You go for repairing. and if it is repairable, that means its impact is such that even if there is a failure, you can definitely identify the fault and you go for maintaining it, and you get back to its original state of health. So that is basically the repair. Now if it is repairable, then and the repair time is almost negligible, that means you have already streamlined this one, okay, and it is done automatically. Suppose in extreme cases, in the best possible scenario, then in that case MTBF, mean time between failure, may be equated with mean time to failure. So later on when we will take up examples, we will again be referring to MTTF as well as MTBF, and the difference, if any, between these two will be explained further. Okay.